Okay, good morning, everyone. Looks like you all got the email, which is good. I think that's everyone. So good. Yeah. I'm under quarantine, obviously, and today is day 7. So we should be able to have class on Monday normally back on campus. I will let you all know if that changes, so just pay attention to your email. I'm going to see if I can get, I don't know if I can go in and get tested. That's the thing, since I'm under quarantine. That's my one question. So I need to figure that out. But as of right now, we'll be back on campus Monday. Any questions before I begin today? We're going to be doing a couple more partial fraction problems, and then we're going to move on to the next section. So are there any questions before I start?
You look so different from when I met you in person. Why is this a thing? Why is this a thing? You look so different here.
Really?
Yes.
I'm not sure. Yeah, I find I'm having the same experience when I meet y'all in person too. It's, you know, what comes through on camera is different. So any questions though over partial fractions? Do you have any issues with the homework that you want to talk about? Any of the problems? Calculator issues? Okay. Well, I've got this nice problem here. This is directly from the textbook. It's an even problem, so I did not assign the evens. So I thought it'd be a good problem for us to work through just to get started. So it is a partial fraction problem, all right? And what we need to first determine is whether or not we need to do long division first. And so we have to compare the degree of the numerator and denominator. The degree of the numerator is 4, right? How about the denominator? What's the degree of the denominator?
5.
5. So you would have to imagine that you would have to take x squared plus 1 and square it. And when you did that, you would get an x to the 4th as the highest power. Now, I'm not going to do it, but I'm just saying if I did, I have to mentally be aware of the fact that that would give me x to the 4th power if I did this. And then I multiply by x, which would give me an x to the 5th. So the highest power of x on the bottom should be 5. And so the degree of the numerator is 4, the degree of the denominator is 5. No long division is necessary, right? So then I need to factor. Well, the good news is that it looks like they've already factored it. The problem is being presented to us factored. So I have one factor here, right? That's linear. And then I have this factor here that is the x squared plus 1 is a quadratic that is not factorable, right? X squared minus 1 would be, but x squared plus 1 is not. So this right here is an irreducible quadratic, right? And more than that, it is squared, so it's repeated. We didn't do one like this in class last time, which is why I wanted to do this one. So how do we handle this? Well, let's do our partial fractions over here. I'm going to do x to the 4th plus 1 on top over the x and then the x squared plus 1 squared. I know that that's going to turn into a over x first because I had a linear factor. So I have some number over x. Now plus. Now last class we discussed, what do you do? What do you put on top of an irreducible quadratic? What do we got?
Linear.
Linear, something linear. So like bx plus c. But here's the thing. It's repeated, right? Now we did do one in class last time. I'll go back to last class. When we had a repeated linear factor, here, when we did this, we had a linear factor here. We had a repeated linear factor. So what we had to do was put the linear factor on the bottom with b on top, then a second linear factor, or sorry, a second constant over that linear factor squared. And I told you what you do is you keep all building up the powers, right? So if it was cubed, you would go, you know, b over x plus 1, c over x plus 1 squared, then there would be a d over x plus 1 cubed. So anytime you have repeated, you have to kind of like repeat the process with additional terms, building up that power in the denominator. We do the exact same thing here. We're going to start with x squared plus 1 here. And then we have to repeat that process. So I'm going to have another linear on top, dx plus e over that irreducible quadratic, but now squared. Does that make sense? And this is pretty much the extent of partial fractions. This is how far we're going to go. You could actually talk about what happens if the denominator has like an irreducible cubic, right? Like we're only going to do linear quadratics on the bottom, but what if it was cubic on the bottom? What do you think? Just what does your gut tell you would have to do over here?
That fx plus g over x squared plus 1 cubed.
Okay, so if the bottom was cubic, right? Look at the pattern. If it's linear on the bottom, we put a constant on top, right? If it's quadratic, we put a linear on top. So the top is always 1 degree less than the bottom, isn't it? So if you had a cubic on the bottom that was irreducible, not factorable, then you would have to put a quadratic expression on top and then put your cubic on the bottom. And if you had a 4th degree that was irreducible, then you'd have to put a 3rd degree on top. So you would actually have something more like fx squared plus gx plus h or something like that. Now we're not going that far. I'm just trying to explain to you that partial fractions, the idea of it can be extended out to higher degrees on the bottom. We're not doing that though. So are we clear on this? Are we good? Can I continue?
Sir, Professor, where does the bx plus c and dx plus e come from?
Anytime you are trying to work with an irreducible quadratic, you always put a linear expression on the top of it. If you're working with a linear factor like the x, you don't put a linear on top, you put just a number like a constant on top. So this is just what you do when you do partial fractions. You always put a linear expression on top of your irreducible quadratic. I don't know if that answers your question. I mean, it's the process of partial fractions. That's just what we do. What would be a mistake is if you put b over x squared plus 1 and then c over x squared plus 1 squared. That would be wrong because you would never get it to work out properly. Okay, I'm going to clear fractions now. So I'm going to multiply left side by this. Okay, and I'm going to multiply the entire right side by that also. Of course, it just goes away on the left. So we get x to the 4th plus 1 equals, now this is going to be kind of complicated. Let's see, here to here, this x cancels with this x, right? So all we're left with is the a, and then also the x squared plus 1 squared. Then when we multiply here to here, I still have the bx plus c, that didn't go anywhere. The x squared plus 1 cancels one of those factors, but I still have one left, and I have the x. So I have an x here, and I have the x squared plus 1, just a single factor. Questions on that? Last one, here to here. I still have the dx plus e. This x is still here, but the x squared plus 1 squared cancels completely with this. And so all I have is the x there. Now, we could try the shortcut method, but I really was hoping that we would just go straight to the long way because I don't think shortcut's going to get us there. So I'm just going to multiply all this stuff out and see what happens. All right, so I'm going to do this yellow first. I'm going to square that. I'm going to do that in my head. I'm trusting you could do that on your own if you needed to. And not only am I going to do that in my head, I'm going to distribute an a through it also. So I'm not showing a lot of this work. It should become a x to the fourth plus 2a x squared plus a. So that's because x squared plus 1 squared becomes x to the fourth plus 2x squared plus 1. And then I just pass an a through it. Is that all right? On this one, okay, I'm gonna actually do, I'm gonna ignore this x for right now. I'm gonna just FOIL this out. So bx times x squared, that would give me, what would that give me? Bx times x squared. That's bx cubed, right? But then I will have to hit it with this x. So I should get bx to the fourth. Then I'm gonna do here to here. That would give me bx times 1, that's bx, but then I would have to hit that with the x, so that should be bx squared. Then I do c times x squared, which is cx squared, but then again, I hit it with the x, so that should be cx cubed. And then the last one is 1 times c, which is c, but then hit it with the x, so that should be plus cx. Am I doing that too fast, or can I trust that you can do that algebra on your own? You okay? All right, last one, just pass this x through. So we should get dx squared plus ex. All right, continuing. All right, let me grab everything, collect like terms. The only thing I have that has, well, I have 2 things with x to the fourth, actually. I have this and that. So I have ax to the fourth plus bx to the fourth. I'm going to write that as a plus b with the x to the fourth factored out the back. Now x cubes, I only have one x cubed term right there. So I have plus cx cubed. Don't really need to factor a c out because it's just a single term. X squareds, I have this one, I have this one, and I have this one. So I have 2a plus b plus d. So I'm going to put that like this. 2a plus b plus d with the x squared factored out. I'm running out of colors here. Let me go with red here. For x, our x terms, I have this one and this one. So I should have plus, in parentheses, c plus ex. And then finally, I have this plus a. Now on the left side, I've got to make the left side and right side balance out. So I have to match the coefficients. So when I look at the coefficient in front of the x to the fourth, it's a 1. So that 1 must match up with this. So I'm going to start writing my system of equations. A plus b must be equal to 1. And I left some spaces here because we know that we have what? A, B, C, D, and E. We have 5 variables in there. So this system of equations is going to, I need to have some spaces. All right, how about the C? What does that C have to be?
0.
0, because I don't have any x cubes over here, right? So C must be 0. All right, then 2a plus b plus d, okay, that's this, has to match the coefficient of x squared on this side. And again, there is no x squared, right? So that has to be 0 also. And then this one says c plus e. So c plus e has to be equal to the coefficient on x. And again, there is no x over here, right? So that must be 0 also. And then finally, the a here has to match up with the constant that's here. So that tells me that a is 1. And that is my system of equations. Now, I think we can get this without actually using our calculators, but again, to practice, I'm going to convert this into a matrix, an augmented matrix. So I'm looking at the coefficients. I should have, what should my first row of numbers here be? For this equation?
Would it be 1 1 0 0 0 1?
1, there you go. So we have 1 in front of A, 1 in front of B, no C's, no D's, no E's, equals 1. That's this. The next equation, I have no A's, no B's, I have a C, I don't have a D, I don't have an E, and equals 0. So it should be 0 0 1 0 0 0. The next one should be 2. Let's see, B, I have 1, C, I have nothing, D, I have 1, E, I have nothing, and that equals 0. And then the next one, I have nothing for A, nothing for B. I have a C, I don't have D, I have an E, and I have that equal to 0. And then finally, I have an A, I don't have B, I don't have C, I don't have D, I don't have E, and that equals 1. There is my augmented matrix. It is 5 equations, 5 unknowns, and now we would do that on our calculator and do our REF or however you want to do it. Let me go grab my calculator. Like I said, we could have done this. We could have done this by hand, probably faster, but you know, in the event that you're taking a test or something and you get a system of equations you can't solve easily, we have to have this way. So while you're doing this and I'm doing this, I will also mention to you, one of your classmates had sent me a nice little link to a video for how to do this on the calculator. And they actually show the screen and stuff. And it's a good video. The only drawback to it was that it doesn't cover all the different types of calculators. It's not every calculator has the same keys. The TI, they've changed their keys a little bit on different calculators. So like my calculator does not have a matrix key. I don't have a key here that says matrix. I have to go into my math menu and then pull up matrix. So that's why I showed y'all how to do it this way. So this is what I'm going to bring in. I'm going to pull up the RREF, my calculator. I'm going to do a bracket to start my matrix, then a bracket to start my first row. I'm going to go 1, 1, 0, 0, sorry, comma, 0, 1, close it, open it, 0, 0, 1, 0, 0, 0, close it, open it, 2, 1, 0, 1, 0, 0. Sounds like a song. And then 0, 0, 1, 0, 1, 0. Last one, 1, 0, 0, 0, 0, 1. Close it, close parentheses. That's what's going into my calculator. Has someone done it? I don't feel like typing it. Has someone done it yet? Anyone? No. What do you get? Go ahead. Whoever. Aaron?
Got 1 for the first one.
Okay. So that means A is 1.
A is 1.
B, the second one is what?
0.
0. C,
0.
D,
-2.
E,
0.
0. Okay, can I get some confirmation? Did someone else get that also?
I got that too.
Yes. Okay.
Yeah.
All right, so it's okay that we got zeros in here. I mean, don't freak out about that. All right, let's go back up. Let's take this and let's go back to what this is supposed to turn into. I want to just kind of paste this in here so you can see it. So what's going to happen is when we go rewrite this, the A is going to become a 1, right? So this is going to become a 1. The B is going to become a 0. It's going to kill that off. The C is a 0 also. So that means this whole thing is gone. All right. D is -2 and E is 0. So the original integral right here, I'm just going to jot it down so we have it. This original integral is going to turn into the integral. We'll have 1 over x. And then over here, we're going to have plus. The only thing left was -2 over x squared plus 1 squared dx. Now, if you don't believe this is true, you could get a common denominator between these two, put them together. And if you do that, you should get this up. You should get this. I'm not going to do it, but that's basically what we're saying happens. If you put these together, you get that.
Shouldn't there be an x after -2?
Oh yeah, I'm forgetting the x. Sorry, thank you. X, thank you. That's an x right there. Very important. I forgot it. Thank you, Aubrey. All right, so we're ready to do that integral. So I'm going to write that, and I'm going to copy it. I'm going to do this on the next page. Any questions? I always have students ask me, like, is there an easier way? And I just tell them this is the easier way. I mean, there's not another way. So, all right, so here we go. Can we handle these? Well, the first one should be easy, right? 1 over x, the antiderivative, that's just natural log of x, right? So we know right now this is the natural log of the absolute value of x plus whatever this integral is. And you know what? All right, I'll leave it. We have -2x over x squared plus 1 squared dx. Any ideas here?
U substitution.
Basic U sub, because 2x plus, I'm sorry, x squared plus 1, the derivative of that is 2x, which I almost have up here, don't I? I almost have that up here. So let's make our lives really nice. Let's kind of like work smart here. Let's just take the negative out of the integral. And then the 2x matches exactly, doesn't it? Like if this is u, that's du up there. So here comes our basic u sub. U is equal to x squared plus 1. The derivative of that is 2x dx, which I have exactly. So I'm just working on this integral right now. So I'm just working on this part, forget the negative for now. This becomes integral. Let's see, this x squared plus 1 is u, so we've got a u squared on the bottom. And then the entire 2x dx turns into du, right? So I'm just going to put 1 du like that. Of course, this is just u to the -2 du. And we can find the antiderivative of that. This is -u to the -1 plus some constant. And that's just -1 over u plus a constant. I just move the u back down. And then u, I replace it with what it was, which was x squared plus 1. So now I'm ready to come back up here. Say, all right, this is equal to natural log absolute value of x minus this right here, right? Which is -1 over x squared plus 1 plus a constant. And I can make those two negatives come together to be a positive. And I think this will be my final answer here. There we go. Questions? I think the big moral of the story here is that if you have an irreducible quadratic that's repeated, like, you know, what it turns into, the fact that the linear thing is on top is vital. So I want to give you an example. We're not going to work through a problem, okay? I just want to make sure you understand how this is all working, okay? Let's say we had an integral, and on the top, let's say we had something. Who cares what it is, okay? Well, let's say on the bottom we had x. Let's say we have x plus 1. Let's say we have x plus 4 to the third let's say we have x squared plus x plus 1. And then let's say we have x squared plus 4 to the third dx. Now, look, I would never give you a problem like this, okay, ever. This is just to illustrate, do you understand what the partial fraction pieces turn into, right? So let me look at all these denominators. I've got linear factor, distinct, right? It's not repeated. It's unique. It's the only one there, x. I have another distinct linear factor, x plus 1. Then I have x plus 4, that's linear, but then it's repeated, right? Then I have this is an irreducible quadratic. And then this is also an irreducible quadratic, but it's repeated. So if I did partial fractions on this, okay, if I did, here's what it would be. Well, does someone want to tell me? Like if I did partial fractions, I would take all of this, right? Take all that and set it equal to, okay, so what would the first piece be?
A over x.
A over x, okay, that would take care of that. Plus, how would I deal with this?
B over x plus 1.
B over x plus 1, okay. Plus, how do we deal with x plus 4 to the third?
You build up to it using just numbers as numerators.
Okay, so like c over x plus 4, right? Then another one, right? D over x plus 4 squared.
Yeah.
Plus another one, e over x plus 4 to the third, right? So I built it out, right? Okay, now I come to this one. It's an irreducible quadratic, right? Doesn't factor. So because it's quadratic and irreducible, I have to put a linear expression on top. So fx plus g over the irreducible quadratic. And I'm done with that one, right? Then I move on to the next one, irreducible quadratic repeated. So I've got to have on top linear, right? I'm going to start running out of letters here. hx plus I over the irreducible quadratic, and then start building it up. Plus jx plus k over x squared plus 4 squared. And then one last one, lx plus m over x squared plus 4 cubed. And that would be it right there, right? Now, I would not want to put those together. I would not want to have to like clear the fractions and, you know, that would be a mess algebraically. But that's not the point of the problem. The point of this is just to show you, this kind of covers all the scenarios. How do you deal with linears? How do you deal with repeated linears? How do you deal with irreducible quadratics? How do you deal with irreducible quadratics that are repeated? Does that make sense? Does that illustration help a little bit? Okay. All right, let's do another one. This one looked interesting to me. Square root of x over x squared plus x dx. All right, first thing. This is not a rational function because it is not a polynomial divided by a polynomial. The denominator is a polynomial, x squared plus x, but the square root of x is not a polynomial. Remember, polynomials have to have positive integer exponents. So, or sorry, non-negative integer exponents. So square root of x is x to the half. And so you can't have fractions in polynomials as exponents. So it's not a rational function. We cannot use partial fraction decomposition. Which means—
Can it all be squared?
Pardon me?
Can it all be squared?
I was hoping someone would ask that, because that seems like that would solve the problem, wouldn't it? Like if we just like maybe squared the top and bottom. I don't know if that's what you're suggesting, Austin, but if we square the
Yeah,
top,
yeah.
we square the top, it becomes an X. We square the bottom, well, then we could FOIL it out, right? That seems like it would solve the problem, but it won't. And here's why. Just think of it this way. If we're trying to find the antiderivative of some function, all right? Right? We're trying to find the antiderivative of this function. Can you just square it? Can I just take this function and square that and get an answer? And it won't be the same. It can't be the same answer. What, right? So maybe you find this answer and take the square root of that answer. I don't know. Let's try it. Let's just see if it works. What is the antiderivative of x dx? What's the antiderivative of that? We know what it is, right? That's just 1/2 x squared plus c. Yes. Okay, so let's try and do this thing that maybe works. Instead of doing x, let's just square it out of nowhere. Let's just square this. What's the antiderivative of this?
1/3.
X cubed plus c, right? So these are obviously not the same, right? We squared this, so maybe we take the square root of that and it'll take us back to this. Does it? No, right? The square root of this is not that. So I guess what I'm trying to illustrate here is, even though it looks like it would be really nice if we could just square this, or square top bottom, you cannot. The only thing you can ever do to an integral is multiply by 1. Okay, that's all you can ever do with the integrand. We've done that before. We multiply top and bottom by something. That you're allowed to do, but you can't just arbitrarily square it out of nowhere.
Could you sub root x for u?
You could do a u sub. We could try that. Now, I'm not sure why you're thinking that. It's the right move. Okay, it's the right move, but what made you think to do that?
Because everything's divisible by root x.
Everything, yeah, somehow these are all powers of x, right? So maybe, right? Maybe if we do this, right? If we make a basic substitution, use root x, let's see what this turns into. Well, what's du? Well, we know the derivative of that, right? 1/2 root x dx, that's the derivative of this. So I can replace this root with u, right? That can be replaced with u. Dx, this doesn't match, right? But what can we do here? What can we do?
You can move it over to the du.
Yeah, because, and this is only special to this problem, because the square root of x is u, I can replace this square root of x with u, right? So I'm gonna get dx by itself by multiplying both sides of this by 2 root x. That's this line. And then I'm gonna replace that root x with u. Understand? So now I know dx, this dx right here can be replaced with 2u du. I know that this root x, right, can be replaced with u. So if I'm starting to build this integral up, here's what it looks like so far. This root x is u over, okay, this dx becomes 2u du. Are y'all following me? What about x squared though? What's x squared? You gotta get everything in terms of u.
U to the 4th.
U to the 4th. So how are you doing that? You take this, you square both sides. What happens if you square both sides? U squared equals x, right? Now square both sides again. U to the 4th equals x squared. So now this u squared becomes, x squared becomes u to the 4th, and then plus this x becomes what? U squared? Now I'm going to put this 2u up here with this. So we should have 2u squared on top over u to the 4th plus u squared du. Don't these all have a u squared? Couldn't you factor u squared at the top and bottom? And
Yes.
cancel it? So if we cancel a u squared from everything, we should just get a 2 over u squared plus 1 du. And if I pull the 2 out, I hope you recognize this. Right? Isn't that formula 17? That's formula 17. That's the antiderivative, that's arctangent, isn't it? So 2 times, what's a for us here?
Just one.
It's just 1. So that's the easiest case because then the formula just becomes arctangent of u plus c. And don't forget, what was u?
Square root of x.
Square root of x. There it is. Well, that seems weird, huh? That seems weird. So this is an example of a problem where you do a basic U substitution. That's weird that they have this problem here. Interesting. All right, let's do another one. X cubed. I like that problem, but the one thing I did not like about it is that we never needed to do partial fractions. X cubed over the cube root of x squared plus 1, not the square root, the cube root. And I want to show you all something real quick before we get into this one. Do you see right here when we did this, we did the substitution u is root x, and then we took the derivative and got this, and then we worked it out, and at the end we got dx was equal to 2u du. I want to just show you a different way you could have done this. In the beginning right here, when we let u be equal to root x, you can square both sides of this equation right now and make this u squared equals x. And now you can take the derivative on both sides. But when you do it, you have to use chain rule. So the derivative of u squared is 2u times the derivative of the base, the derivative of u itself, which would be du. And then on the right side, the derivative of x is 1 dx, or just dx. Do y'all see how you get the same thing? 2u du equals dx. It's just another way you could have done this. I just wanted to make sure you had seen that. Okay, why don't I give you a minute on this and see if you can figure out what to do. Let me warn you though, you cannot use trigonometric substitution. I know, remember with trig sub, we were always looking for like square root of something squared plus something squared or minus something, right? It was square root, previous section, right? It was square root, this cube root, can't do it, all right? So see if you can't figure out what to do. I'll give you a few minutes. Well, how's it going? Anybody figure out what might work? I've never done this problem, but I have an idea of what might work. You want to go through it?
Yeah.
Hey, somebody asked in the chat, I just saw it, someone had asked back when we were doing the previous problem, how can you tell that a quadratic is irreducible? Does anybody know an easy way to check whether or not a quadratic is irreducible?
If b squared minus 4ac is negative.
Yeah, so remember the quadratic formula? X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. That's a quadratic formula. This gives you the solutions to any quadratic equation like that. In this formula, the b squared minus 4ac, okay, is called the discriminant. And the discriminant here is, if this turns out to be a negative number, then there's not going to have real solutions. If it had real solutions, then you could factor it. It would break down to be, you know, something times something equals 0. If, as long as this is bigger than or equal to 0, you're going to have answers. So one quick way to check it is to look at this b squared minus 4ac and see if it's negative. If it's negative, it's irreducible. So if you look at this right here, our numbers are 1, 1, and 1. And so b, right, b is 1, a is 1, c is 1. So if I try this right here, b squared would be 1 squared minus 4 times a, which is 1, times c, which is 1. This is 1 minus 4, this is negative 3. And that tells me that I don't have any real solutions, which means it's not factorable. It's irreducible. So that's one quick way to do it. Good question. Okay, back to this. All right, so what I'm feeling, and I'm not sure if it's gonna, I don't know if it's gonna work, but what I'm feeling here is that I'm gonna make a basic u sub of u is x squared plus 1. Now, let me tell you why I'm thinking this. In my head, I was thinking, well, if that's what u is, then I can actually solve this and have an equation for x squared, can't I? And maybe with that, I can get this. Let's see. Let me take the derivative. Du equals 2x dx. And this problem is actually, I don't even think we're going to need partial fractions for this either. We're not. Bye. Okay, so I'm going to multiply both sides by a half. Does anyone see what I'm about to do? Do we have x dx? Do we have x dx anywhere?
On top.
On top, right? I can just rewrite this as x squared times x, and that x dx can go together. So x dx is half du. Now see that x dx right there will be the half du. The u squared, sorry, x squared plus 1, that's u. And then the x squared is u minus 1. Right? That's kind of boring. Let's see. Let's just keep working here. Maybe we will need partial fractions. So what's the top turn into? Sorry, I forgot. What's the top?
U minus 1.
U minus 1. And then over the cube root, right? The cube root of x squared plus 1, which is u. And then times x dx, which is half du. Yeah, this is not going to need partial fractions. Maybe it's the way I did it. I don't know. Because this becomes u minus 1 over u to the 1/3. And can't I split that up into two fractions now? because I have u minus 1, 2 terms on the top and 1 on the bottom. I'm very disappointed. This becomes u to the 2/3 minus u to the negative 1/3 du. Y'all get what I did there? U over this and then negative 1 over this, split it into 2. That sucks. I thought this was gonna. I thought this was going to give us something. Maybe if we do it a different way. I don't know. I mean, we got it. We're there, but I'm just kind of disappointed because this is in the section for partial fractions. I was really thinking this would turn into a partial fraction problem, but it hasn't. Okay, the antiderivative, let's just finish it. The antiderivative of this, add 1 to that, I get 5/3, so 3/5 u to the 5/3 minus 3/2 u to the 2/3, adding 1 up there, plus c. And then I'll distribute the half through, we'll get 3/10 u to the 5/3 minus 3/4 u to the 2/3 plus c. And u was x squared plus 1. And I'm bummed out. I mean, you could argue that this was just a complicated u substitution problem, right? I mean, there was really nothing else we needed. All right, questions on this one? One last one, and then we'll move on. Okay, this one, integral x arctangent of x dx. All right, so we look at this, and this doesn't look at all like it has anything to do with partial fractions, right? We go back and we think, okay, basic u sub. If you did a basic u sub here, what can you do for a basic u sub? I don't think you could do anything that's going to be worth it, right? Anybody have like some sort of instinct as to maybe how to go about this?
By parts, maybe?
By parts, integration by parts, maybe? That seems fair. If you did parts though, what would your u and dv be? Remember, you have to choose a u, you have to choose a dv here. I really want to make, yeah, I want to make the x u. Okay, that's what I'd like to do, right? I'd really like to have x here because then the derivative of that's just dx, right? Problem with that is that forces me to put the arctan here. And then I have to integrate arctan, which I don't feel comfortable doing. Well, I mean, we could do it, but that would be a whole new integration by parts problem. So it might be easier for us to do it this way. Do arctangent here, because I know the derivative of that. Put the x dx here. When we take our derivative, we get 1 over 1 plus x squared. We should all know that's the derivative of arctangent of x. And then what do we get when we integrate here? What's b?
1/2 x squared.
1/2 x squared, right? So I'm starting to look at what voodoo is going to be, this diagonal. And it's not looking very pretty, but it is going to be a rational function, right? It's going to be like the 1/2 x squared on top of this. And I should be able to do partial fractions on that. So let's continue with the ultraviolet minus voodoo. Ultraviolet are these two multiplied. So I'm going to put 1/2 x squared arctangent of x minus the integral of voodoo. So these two multiplied. I'm going to take the 1/2 that's in front of the x squared and just pull it outside the integral. And then I'm going to multiply 1 over 1 plus x squared times x squared, and that'll give me x squared over 1 plus x squared dx. Is that clear to everyone? move this to the side. Just get it out of the way here. In fact, I think I'm going to move this down here instead. There we go. So there's our integration by parts. And we look at this last one here and we start thinking, is there anything we can do, right? Is there anything we can do? Well, it's a rational function. So how would we handle that problem? I'm going to just do it as its own problem here. What would be our first step?
Could divide it.
Long division, right? They have the same power, don't they? So since they have the same power, I take the x squared, I divide it by x squared plus 1. And so I'll need to multiply this by 1. That gives me the x squared when I multiply here, and then a 1. Come through and subtract. So I get -1 there. These go away. And now x squared plus 1 can't turn into -1, so that'll be my remainder. So I'll put plus my remainder over my divisor. So this integral now becomes the integral of 1 plus, or I'll say minus. Is there a question? No? Can we integrate both of those? Yeah, first one's easy, right? Antiderivative of x is 1. I'm sorry, antiderivative of 1 is x. And then minus, I hope you recognize that, that's arctan x. Plus c, all right. So I'll go back up here and let's put our answer in here. So we have 1/2 x squared tangent inverse of x minus 1/2, and then this answer right here. So in parentheses, x minus arctangent of x plus c. That should be our antiderivative. We could pass the 1/2 through there, okay? I think I will. I'm going to do it. 1/2 x squared arctangent of x minus 1/2 of x plus 1/2 of arctangent of x plus c. This is the antiderivative. You don't have to pass that -1/2 through. I just did that because I'm actually going to check our answer. I haven't checked our answer in a long time. I'm going to check the answer by taking the derivative real fast. And I mean real fast. So here we go. Derivative of this, I have 1, 2, 3 terms. I'll do them individually. The first term has a product right there, so I'm going to run the product rule on this. The derivative of this first one is just going to be x, because the 2 comes out, gets hit by the 1/2, power comes down, arctangent x. I think I might need a little more room. Okay, and then plus now the derivative of arctangent of x, which is 1/1 plus x squared, times the first function, which is 1/2 x squared. Okay, done with product rule. Move on to this one. Derivative of that, -1/2. Okay, derivative of this is going to be 1/2 times the derivative of arctangent of x, which is 1/1 plus x squared. And of course, derivative constant is 0. Yeah. What are we trying to get to? I forgot. This needs to turn into x inverse tangent of x. Clean up maybe a little bit. X. Somehow this is all supposed to go away. Something doesn't look right. We didn't. I'm just double checking. Yeah, no, I think we're good. Let's just keep going here. X arctangent of x plus, okay, when I put these two together, I'll have x squared over 2 and then 1 plus x squared. This doesn't look right, y'all. 1/2 times 1 plus x squared. Y'all see what I'm saying? This doesn't look like it's going to come to 0. Let me see. These have the same denominator, so I can put those together. Let's do that. So if I put this one and this one together, I get x squared plus 1 over 2 times 1 plus x squared. And then I still have minus a half. Oh, yeah, this is where it happens. Here we go. Oh, those cancel, dumbass. Okay, those cancel. There we go. Right, x squared plus 1 plus x squared cancel. That's a half minus a half. Those go away. All right. Sorry, I didn't see that right away. There we go. X arctan x. Oh, geez, it's been a heck of a week. Okay. All right, I think I'm done with this section. I think we're done with techniques of integration. So good for us. Now, I mentioned this before that everything we've been doing is out of chapter 6, okay, which is, we do it backwards in this class. The way that the book does it is in chapter 5, they teach you what's called the fundamental theorem of calculus, FTC, the fundamental theorem of calculus. They teach you that in chapter 5. And then they do applications. Okay, that's all in chapter 5, applications. And then you get to chapter 6 and they do the techniques of integration. So they teach you how to find the antiderivative of more complicated things, which is what we've been doing. Right, that's the way most textbooks work. Hey, we have this fundamental theorem of calculus. Oh, let's do some applications of it. And when we're doing this here, we're doing antiderivatives, but they're very simple problems. They're not complicated. And then they say, oh, what if our functions are more complicated? What are our techniques? At Northwest Vista, we always do this first. And I'm not sure when we agreed upon this as a faculty because we said, look, let's get this kind of harder stuff in the beginning. And then when we do this, this will probably seem a lot easier now when we do this, because you know how to integrate hard things, but the problems you're going to see from here on out, the integrations are going to be easier in the application problems, which will be good. Also, I think it's that we want to know right off the bat, like in the beginning of the class, like, you know, are you up to the challenge of this class? Because it's, a lot of students can get through this chapter 5, but then they hit 6 and it's like a wall, you know, and we're already, what, how many weeks into the semester now? So we'd rather 6 weeks. So we'd rather kind of know early, like where you are. That's why we do the chapter 6 first. Okay, so we are going to take a step back now. All right, you ready? Why have we learned how to find antiderivatives? What is this all about? So we are going to start this with some geometric motivation. So I'd like, if you can, try and just clear your mind, all right? You've got all these techniques that we've learned, all right? All these techniques that you've learned, but now let's just know they're there and just clean the slate and just start talking about just general ideas of geometry and math, all right? So the motivation of everything here comes from the area problem for a circle, right? If you go back and you think about historically, right, humans were trying to figure out, can we find a formula for the area of a circle? I mean, we were comfortable with rectangles, right? We said, okay, if we have a rectangle, we can define, like if this is width and this is length, we can define the area to be the length times the width. And so we were fine finding areas of rectangles. But when it came to something that was curved like a circle, we didn't have a formula for it. Now, we all know now that the area of this is pi r squared, right? But that was not known. That was not known. So how did they come up with that, right? How did we humans come up with this formula for this? Well, the first attempts at trying to do this were a technique called the method of exhaustion. Okay, so they literally took a circle and started like putting squares inside of it and rectangles and filling in all the gaps and just adding up all those areas together to try and get an approximation for what that area was. And they would just, I mean, they would get a really precise circle drawn and really precise ruler, and they would measure, and they would get pretty close to the true area. And that's how they first started doing it. It was a pain in the butt. And then later on, they said, well, you know, instead of drawing those, why don't we do this? Why don't we take a circle? Why don't we start drawing triangles maybe in it like this, right? And just put more triangles. Okay, we can just put more and more triangles in here and estimate, you know, we can find the area of a triangle, right? We had formulas for that. So this became a pretty good way of approximating the area. And it's like the smaller your triangles got, right? The smaller they got, the more you would have in here. And we'd have to zoom in to see this, but if you go try and zoom in here, let me see if I can actually get there. I don't know if I'll be able to. Yeah, I think I did too many triangles. You can't see here. Yeah, you can't see. There's some gaps in there. There we go. There. So if you zoom in enough, right, even if you had 1,000,000 triangles in there, you would have some little gap because this is curved, right? That's curved, and this line is straight. So you're always going to have some little error, right? There's going to be some error no matter how many triangles you ever do, right? But you could get pretty damn close if you were willing to draw a lot of triangles in there. So that's kind of the motivating idea for what we're about to do. This idea of approximating an area with some shapes and having some error. So I'm going to skip through all this. The big question became after the circle is, how do we find the area underneath just an arbitrary curve, right? If I just give you an arbitrary curve, how do you find the area underneath it? Right? If I just give you this and I say, okay, you know, start here at A, go to B, can you somehow find that area? If this is not a straight line, can you do it? And so what we did is the same sort of technique that we did with the circle. We put a bunch of rectangles in there and we started adding up the areas of the rectangles. And we would have error, right? Like if I added up these rectangles, we would have all this right here would be an overestimate, right? That would be too much. If we added those rectangles up, that would be more area than what's underneath the curve. But we could get more precision if we were able to make our rectangles smaller and smaller, more narrow, right? So that's what this idea is. If we have a curve, we could do these rectangles. If we start putting more rectangles in there, the error starts to go away, right? We start to get a better and better approximation if we put more rectangles in there. If we only have a few, we're going to have a lot of error. But if we have a lot of them, we get real close to the true answer. So we went through this, and it was, you know, this long drawn out thing. And I could spend the next 2 weeks showing you how to do this by hand, like show you the formula. They're called Riemann Sums. And it's a way of actually by hand calculating approximate areas underneath curves. But ultimately, when calculus came around, calculus was able to finally solve the problem, because calculus has what in it, the heart of calculus has the limit, right? And the limit is something that allows us to let things get really, really, really small without actually getting there, like go to zero without getting there, or we can actually let things go to infinity. So if you look at this picture and you think about what the true area of this would be, you know, this is the approximate area, right? That's an approximate. The true area would be if I could let the number of rectangles in here become infinite, right? If there were an infinite number of rectangles, then the width of each rectangle would become infinitesimally small, right? The width. Eventually to the point that it's basically a straight line up and down. And so you're somehow adding up all these little infinitesimally narrow strips, and that should converge to the true answer. In the limit, it should go there. Does that kind of make sense to everyone? We are not going to go through the mechanical part of that, okay? Because it is truly torture, and time-wise, we're not going to. If you want to learn how to do Riemann sums, I'm very happy to sit down in my office with you, and we can, or office hours, and I can just show you. You know, I even have the formula here for you if you want it. You know, this is the general formula for Riemann sums right there. It's a limit, an infinite sum. Okay, so we're going to circumvent all that, and I'm just going to tell you that the idea here again is that if we want the true area, okay, if we want the true area, what we need to do is we need to add up an infinite number of rectangles, right? An infinite number of rectangles with a width of, okay, well, let's just take an arbitrary rectangle in here. How wide would this rectangle be, right? Well, we're going to make these smaller and smaller and smaller and smaller and smaller, right? Smaller and smaller and smaller. So this distance right here, this width of this rectangle is basically an infinitesimally small measurement of x, right? Infinitesimally small measurement of x. We like to use delta x to represent that, like a change in x. It's just a very small change in x is how wide it is. Now, delta x is how wide they are, and the height of the rectangle is, well, this some point on this graph, right? That point lives on this graph. And so it would be, the height would be what I get when I plug some point here in that little rectangle into the function. That would be the function's height at that point x. That makes sense? If I move to a different x over here, my height's going to be different, but it is all determined by that function. So to find the true area, I want to add up an infinite number of rectangles that each have a width of delta, or yeah, delta x, and the height, that's f of x. So that means that the area of each rectangle is what? Well, length times width, right? So how tall is each rectangle?
F of x.
F of x, and how tall is it? I mean, sorry, how wide is it?
Delta x?
I'm calling it delta x, right? That's one rectangle, right? That's just one of those rectangles. And we want to add them up, right? We want to add them up. We want to add an infinite number of them together. So we want to somehow add, so we use a summation. We somehow add all of these areas up, right? We add an infinite, we add all these rectangles up to get an area. And the key to the calculus part of that is that we let the number of these go to infinity. Okay, so we want to let the number of rectangles go to infinity. When we do that, things change in terms of our notation. Instead of using this, so as we let the number of rectangles go to infinity, our notation changes. And we switch to, I'm running out of room here. We switch to this notation. So this notation looks familiar, right? This integral sign was just a symbol that we used before, right? It was just a symbol that told us go find the antiderivative. But now what I want you to see is that the symbol actually comes from this sigma. Sigma is the Greek letter S, capital S. When we let there be an infinite number in this summation, an infinite number of rectangles, we had to come up with some notation to let you know we were letting everything go to infinity. And so what we did is we took just the regular letter S for sum, and we stretched it out. When we stretch out that letter S, it looks like this, right? So this integral sign is just an S that's been stretched. That's the symbol for the infinite summation of these rectangles. The f of x is the height of the rectangles, and the dx is the delta x, is the width of the rectangles. The A and the B are where we start and where we end on the x-axis. So if I wanted to find the area underneath the rectangle in this particular example between 1 and 5, then this would be A and this would be B. Okay, I know this is all somewhat confusing, perhaps. I don't want you to get caught up in all the little nuances of how we get from here to here. It's purely a notational thing, all right? So we need to understand, what we need to do is understand what this means, what this notation and the symbols, what they all represent physically in a picture. It's going to be vital for us in this chapter 5 for us to understand how each element of this notation represents something physically in our geometric problem. So I'm going to go back to our notes real quick, clear this out. So this new notation means basically that if you have a function and you started at A and ended at B, and you take your function here, wherever it starts, wherever it ends, and you want to know what this area is, okay? If you want to know that area, we'll call it A, that's all of this. Then what you need to do is you need to cut up that region into an infinite number of rectangles and measure the area of each one. So the notation that tells you to do that is this. Okay, I'm going to take this sum of an infinite number of rectangles. I want to start at A and end at B. So A and B are going to be these two endpoints. And then what am I adding up? Oh, the areas of the rectangles. That's the height of the rectangle times the width of the rectangle. Okay, this is what A is. Does everyone understand this is just notation? That's all it is right now. It's just a way of me telling you, hey, finding this area is equivalent to doing this sum of a bunch of areas, infinite sum. Yes? So when we were trying to do this, like I said, we did Riemann sums. The problem with Riemann sums is that you could only do a certain number of rectangles. You couldn't do an infinite number of them. With Riemann sums, you could do 10,000 rectangles and get an answer, but it wouldn't be the true area because it's impossible for us to do an infinite number of things because you just run out of time, right? Like you have to stop at some point. So we just sat here and said, okay, well, this is the notation for it. Okay, if we can ever do it, if we could ever figure out what this is and do an infinite number, that would be the true area. Well, then came along the fundamental theorem of calculus, which is a theorem that was proven to be true that we can use to actually find this true area. And this is the amazing part of calculus, is that this theorem, that if you want to know what this is, okay, if you want to do this, you actually don't have to go. This is called the evaluation theorem. I have this written in my notes. Okay, I can show it to you in a minute. The evaluation theorem. This is a version of the fundamental theorem of calculus. F TC. Okay, fundamental theorem of calculus. There's two versions of the fundamental theorem of calculus. I'm showing you one of the versions, which is called the evaluation theorem. So here's what the evaluation theorem says. If you want to find that area, okay, and do this infinite sum of rectangles, then amazingly, it will just be capital F evaluated at B minus capital F evaluated at A, where capital F is any antiderivative of little f. And this is big time right here. This is huge. We don't have to prove the theorem, okay? In this class, we don't have to do the proof. If you're a math major, then you will prove that theorem at some point in your life. Okay, but we are going to use it. So basically all this is saying is that if you want to find the area under a curve, all you have to be able to do is figure out what the antiderivative is. And then we've been spending the last 6 weeks doing that basically, right? So now we get the opportunity to use that, what we've learned, to actually figure out something geometrically. So that's the theorem. Now I'm going to show you a similar version of this with one thing added. There's an intermediate step when we write this theorem out. There's an intermediate step that we like to put in here that doesn't make sense right now, but it will make sense after we work through an example. So this piece right here that I just added, just write it down, and then as I do an example, you'll hopefully understand what this thing means. All right. Y'all ready to do our first example of this? I know a lot of you have seen this, okay? In Cal 1, a lot of times we get through this in Cal 1, the beginning steps of this. So let's do our first example, and we're gonna do something that we can actually check. So I'm gonna go and have us look at this function, f of x. I wanna say find area under f of x, this function f, on the interval, let's go 0 to 3. And here's the function, f of x equals x. That's about as simple as it gets when it comes to functions, right? Well, I guess you could argue there's some easier ones out there, but this is a pretty simple function, right? So geometrically, I imagine that I have my x and y axis. I have my function f here that looks like the diagonal. That's f of x equals x. And I want to look between 0 and 3. And I'd like for us to find this area right here. Okay. Now, I did this problem specifically because we can actually answer this question without calculus, can't we? Without any calculus, we can answer the question. Because we know that this point right here is 3 units high. So we basically have a triangle, right? That has a width of 3 and a height of 3. And we know that the area of a triangle is 1/2 base times height, which should be 1/2 3 times 3, which should be 9 halves, right? Or 4.5. Y'all agree that that should be the area of this triangle, 4.5 or 9 halves, without any calculus? But now let's use calculus to verify that that's true. So the theorem says that what we need to do is we need to find the sum of an infinite number of rectangles between 0 and 3 of the function x dx. So I replaced a and b with 0 and 3. I replaced f of x with the function in question. Dx will always be here. And then this must equal, now let's look at this intermediate step here. Capital F of x is any antiderivative of x. So can somebody give me an antiderivative of x?
1/2 x squared.
1/2 x squared. How about 1/2 x squared plus 2? Would that work too?
Yes.
What about 1/2 x squared minus 9? That would work also. Any 1/2 x squared plus any constant would work, right? Or minus any constant. That would be an antiderivative of x. Agreed? Take the derivative of this, you get this. Yeah? Agree? Yes? Okay. You sure?
Pretty sure.
Limited,
What do you mean?
like to 0 and 3.
Oh, but the antiderivative, adding a number just moves it up and down.
Oh,
It doesn't move it left and right. So it'll still be within 0, 3.
Okay.
So this fundamental theorem of calculus says that the area will be equal to this, where f is any antiderivative, right? Any. I can use any one that I want, all right? So I'm going to use the one that has 1/2 x squared plus 0, which means it's just 1/2 x squared. Okay, so that's me. So what I'm doing right now is I'm writing down what the antiderivative is. Okay, I'm writing it down. That is the antiderivative I'm choosing to use. The next part of this, I draw a line here and I put my two numbers. These are my two endpoints. This is known as an evaluation bar. It's a bar. It's to remind you that you still have work to do. We have found the antiderivative. What we need to do now is plug in the two endpoints into the antiderivative. So I need to take my antiderivative and do this part first, and then this part. So what would capital F of B be for us? We are plugging what number into this function?
3.
3. So this will be 1/2 times 3 squared. And then here we're plugging a into the function. A for us is 0. So 1/2 times 0 cubed, squared, sorry, right? And 0 squared, of course, is 0, so that goes away. And this is just 1/2 times 9, which is 9/2, which matches the answer we got here, right? So just because it matches doesn't mean that you could say it's always true. It could have just been a coincidence, but the fundamental theorem of calculus absolutely guarantees us that this is the case. All right. So let me get to some stuff here. We need evaluation theorem. Yeah, I'll get back to that. Okay, so just so we're clear, when we've been doing this is what we just spent about 6 weeks doing. This is called an indefinite integral. Every answer we've gotten pretty much has been some antiderivative plus a constant, right? That's what it's been. This is called an indefinite integral. Now we have this new thing that looks like this. We have these numbers now that are going to be placed above and below that integral sign. Then this. This is known as a definite integral. And our answer should be a number, right? Because it's going to represent the area underneath the curve. And so the way I remember it is that, you know, if you get a number, then you definitely have an answer, right? You definitely have a something. If you do this, you got this function plus c, which is a family of functions, right? Family of functions. So you're not quite sure which function, right? It's indefinite. It's not exact. It's indefinite. but on the right, it's something completely different. So the only difference in the notation are these two numbers, right? That's the only difference in notation. But they give you completely different answers. One of them gives you a family of functions, the other one gives you a numerical value. These numbers are called our limits of integration. Okay, those are the limits of integration. The one on the bottom is called the lower limit, and this one's called the upper limit. Now, on the x-axis, right, on the x-axis, normally A is to the left of B. So you put A here, put B there. Now, I want us to look at something. Give me a minute here. I'm going to go to Desmos. Let me graph something for us. Let's look at that function y equals x. That's the function we were just looking at. I only want to look at it between 0 and 3. Okay, so that right there. And we wanted to know the area underneath that, right? What the fundamental theorem of calculus says is that to find that area, what we need to do is look at the antiderivative, which was 1/2 x squared, right? And we need to look at that what did I just do? There we go. So we want to find the area under, oops, wrong color. Under here, right? We want to find the area under there for this function here, f of x equals x. The fundamental theorem of calculus says all you have to do to find that area is go and take a look at any of its antiderivatives. And then go to 3, go to that point, find the y value there, which in this case should have been, yeah, 4.5, because this is 5, right? So that right there is 4.5. Take that answer, subtract from it the y value at the other endpoint of the blue function. And the y value here is 0, isn't it? And that will give you the area. So the area underneath the red one is just the difference of the y coordinates of its antiderivative. Now it said this would work for any antiderivative, right? So what if I would have done, instead of 1/2 x squared, 1/2 x squared, let's say +2, right? What if I did that instead? Does that change anything?
No.
No, it doesn't, because if I want this area right here, the fundamental theorem of calculus says, oh, find the antiderivative, which is in blue, measure the height of this point, which now is 6.5, and subtract from it the height at this, which is now 2. So take 6.5 and subtract 2, I still get 4.5, right? I don't know, to me, that's amazing. I mean, the fact that to find the area under this curve, you just need the 2 y values off of the endpoints of the antiderivative, to me is amazing. And that's why it's a fundamental theorem of calculus, because it is such a huge accomplishment to have that theorem. So you can find the area under any curve, so long as you can find the antiderivative, right? So let's do something else. Let's do something, I guess, a little more interesting. I'm wondering how far we should push. I feel like pushing pretty far. Let's do this, okay? Let's do this. I want us to show the area of a circle of radius 3 is what? What is the area of a circle of radius 3?
Pi 9.
9 pi.
9 pi. Now, you're not allowed to use the area formula, okay? I'm going to help you through this. Ready? I'm going to start by drawing a picture. I'm going to draw a circle of radius 3, and I'm going to center it at the origin. You know what? I should probably bring in my, yeah, let me just start this over. Okay. Circle of radius 3. Okay, that's the worst circle ever. All right, so I need to somehow show that the area of this is 9 pi. Okay, the only thing I know, the only thing we know at this point is how to find the area underneath a curve, right? We can do that so long as we can find the antiderivative. So is this circle a curve? Is it a function?
2 functions.
Yeah, it fails the vertical line test, doesn't it? Doesn't this fail the vertical line test? So it's not a function. However, it does have an equation. Do you all know the equation of this circle? The equation of it? I'll give you a hint. Remember this from one of your previous math classes? Algebra, probably.
X squared plus y squared equals 9.
Yep. So this is the general formula for a circle that has a center of HK and a radius of R. Does it look familiar? Okay, for us, if I center this at the origin, then H and K are both 0. And then the radius would be 3. So the equation of this circle should be x squared plus y squared equals 9. Y'all buy that? Now, if I solve this for y, I can move the x squared over, subtracting it on both sides. And then I can take the square root on both sides, which means I have to do plus or minus. And I get this, right? Now, it's kind of interesting to note this. And I'll just show you real quick when I'm going to come over here and graph it. I got 2 answers, right? Positive square root of 9 minus x squared. And then I have negative square root of 9 minus x squared. So the positive one draws the top half, and the negative one draws the bottom half of the circle. So if you look at them individually, right? Individually, you have 2 functions, right? But they are functions individually. You put them together and it's not a function. But I just wanted to show you it does draw our circle. So the way I'm going to do this is I'm going to, and see if you agree with this. This top one right here, do it in green. This top one in green, I can draw that using the function y is the square root of 9 minus x squared, right? I can do that. Just the green one will be drawn. And how about we do this? How about we find the area just in the first quadrant? Why don't we try and find the area just in that first quadrant? Whatever that area is, if we multiply it times 4, it should be the area of the whole circle, shouldn't it?
Yes.
The whole circle. So can we find the area of just that one piece? Well, to do the area, we need the definite integral, right? So this area, that area alone, should be the integral from where to where. So imagine these rectangles in here, right? There's an infinite number of rectangles that we're going to draw in here. Where do the rectangles start? Where do they stop?
0 to 3.
0 to 3. So those are our limits of integration. What is the function that we are actually integrating? So the height of the function is dictated by what? All these points on the rectangle are dictated by what function?
The square root of 9 minus x squared.
Square root of 9 minus x squared. That's how tall they are. How wide are they? Well, dx, right? Dx is the width, that infinitesimal width of each rectangle. You following me? All right, there you go. All you need to do is find an antiderivative and you're in business. So do you know the antiderivative of this function? So maybe it's a good time for us to go over here and say, all right, I need to find the antiderivative of that. So let me look at it as an indefinite integral first and see if I can do that work. So this is where you do a drum roll and you see if anyone in the class knows how to do that.
Trig sum.
Trig sub, right? A squared minus x squared underneath the square root. Trig sub, this is section 6.2, the second half of 6.2. Yeah, the second half of 6.2, trig sub. So we're going to do trig sub. What is the trigonometric substitution that we're going to make?
X equals 3 sine theta.
X equals 3 sine theta, good. So we're looking at the fact that we have a squared minus x squared. Whenever you have a squared minus x squared under the root, you make the substitution x is a sine theta. Now you do your dx, which is 3 cosine theta d theta. You also figure out what the square root of all that crap is going to be. What is the square root of all that crap going to be? This is where you either had to memorize it or you have to like grind it out each time.
3 cosine theta.
3 cosine theta. Good. And now you rewrite the problem. The square root part turns into 3 cosine theta. What does dx turn into?
3 cosine theta d
3
theta.
cosine theta d theta. I can bring the 3's out. 3 times 3 is 9. 9 integral cosine squared theta d theta. How do you handle cosine squared? Drum roll.
The reduction formula.
Reduction formula, you reduce it, right? You use the power reducing. So when you do that, you're going to wind up doing 9 integral. This turns into 1/2 1 plus cosine 2 theta d theta. So I'm just using the fact that cosine squared theta can be rewritten as 1/2 times 1 plus cosine 2. See, we've done all this, haven't we? This is a really good problem because it's bringing everything together. Okay, let's pull out the half. So 9/2 integral of 1 plus cosine 2 theta d theta. Hey, we can do the antiderivative of each of those, can't we? 1 and cosine 2 theta. So I'll have 9/2. Okay, antiderivative of 1
Theta.
theta. Antiderivative of cosine 2 theta.
1/2 sine 2 theta.
1/2 sine 2 theta. Right? Plus c.
C.
Now, we ran into this before back in 6.2, where we would come in with our reference triangle at this point, but then we have this problem that sine 2 theta. Remember, because our triangle is all about theta, but our trig thing here is sine 2 theta. But I'm going to do the reference triangle anyway, right here. We know that sine theta is x over 3. So when I draw a right triangle, I get x here and 3 here, and that forces this third side to be square root of 9 minus x squared. Right, we've done this before. So what did we do with this sine 2 theta to make it nicer?
Double angle formula.
Double angle formula. We turn that into 2 sine theta cosine theta. And then the 2 out here and the half kill each other off. So my next line should be 9/2 theta plus sine theta cosine theta plus c. And I think I'm ready to plug everything in. 9/2. What's theta? Theta is the one that's tricky because you can't use your triangle. You have to figure out what theta is, right?
The sine
Right.
inverse.
Sine inverse. You take that, you do both sides sine inverse. So you take the inverse sine on this side, you get theta, inverse sine on this side, you get this. So theta is inverse sine of x over 3 plus sine of theta for us is x over 3 times cosine theta, which is the square root of 9 minus x squared over 3 also. Questions? We're getting close here. So all I did here on the last step was distribute 9 halves through here. And then here to here, because I had 3 times 3 on the bottom, that's 9. It'll kill off this 9. I'll still have the half. This is the antiderivative, right? That's the general antiderivative. Now I'm ready to go answer the question because I have the antiderivative. So I'm going to take this answer, okay? I'm going to come back up here and I'm going to continue with this. I'm going to do it. I'm going to bring this and bring it down here. Probably going to need to go to the next page. So using the fundamental theorem of calculus now, I know that this will be equal to the antiderivative, which we just found to be 9 halves arc sine of x over 3 plus 1/2 of x square root of 9 minus x squared. That is an antiderivative, right? That's the one where I'm not doing plus c, I'm doing plus 0. I can use any one of them I want. So I'm always going to use the 1 plus 0, always. And now the evaluation bar, 0 here and 3 here. So that intermediate step, this step right here, just gives you an opportunity to write down what the antiderivative is before you go plugging numbers into it. So it's just like a placeholder, just kind of a place to put your work. Now it's time to plug in. So I like to do this. Anytime I'm ready to do this last step, I always remember like this first part is capital F with B plugged in. This is capital F with A plugged in. So I do these kind of separately and then I subtract. So let's plug 3 in. You ready? 3 goes first. We're going to get 9 halves inverse sine of 3 over 3 plus, okay, do y'all see what happens if I plug 3 in here? You see right there, 3 squared gives me 9 minus 9, which is 0. And do you see that that kills all this off? So I just get 0 here. Yeah. Now I plug in 0. So if I do that, I get 9 halves arc sine of 0 over 3 plus, and again, see what happens when 0 goes in right there? Right in this piece, right there. It kills everything here again. Now the fun part, we're almost there, we're almost there. This right here is really saying the inverse sine of 1. So go back to pre-cal. Think about the unit circle. At what angle is your y coordinate, because we're doing arc sine, where's your y coordinate 1?
Pi over 2.
Pi over 2. So this becomes 9 halves times pi over 2, right? Minus, okay, how about this right here? This is inverse sine of 0. So again, you go to your unit circle and you say, at what angle is the y coordinate 0?
0.
0. So this is 0. So 9 halves times 0 gives you 0. So this is minus nothing. So we get over here 9 pi over 4.
But that's a quarter circle.
That's only 1/4 of the whole circle, right? So you have to remember what we were doing here. We had gone and said, hey, let's go find the area of this. And we just found that that is 9 pi over 4. So if we want the whole circle, right, we just take that 4 times 9 pi over 4. The 4's cancel and we get 9 pi and we are done. What do you think?
That's cool.
You know what's cooler? Doing this. Show the area of a circle of radius r is pi r squared. How would you go about trying to do this? Draw me a circle first, right? Of radius r. Do you know the equation of that circle? X squared plus y squared is r squared, right? We don't know what r is this time. R is some fixed number. Can you solve this for y?
Yes.
Sure, plus or minus square root of r squared minus x squared. So it's the same setup as what we just did, except we don't have a 3. We just have an arbitrary number r, right? If we look at just the top half of this circle, that's drawn by the one that's positive. Then we can go and do the same thing and try and find the area here. What would your definite integral be? Where do your rectangles start and where do they stop? Be careful. Where do they start and where do they stop?
0 to r.
0 to r, right? It was 0 to 3, but now it's 0 to r. And the thing that you're finding the antiderivative of is not 9 minus x squared, it's r squared minus x squared dx. Well, how would you do this? Trig sub, right? Trig sub. So your trig sub would be x is, see the r here is arbitrary now. So what's that?
Oh, I just checked the time and it's 10:50
Oh shit.
and I have a class at 10:45.
Man, I'm so sorry. I was just going and going, man. To me, it felt like we'd only been here half the time. I've had a really weird week, man. My timing is all off. Sorry, thank you for letting me know. If you gotta go, you gotta go. I would encourage you to make sure you've done all the 6.3 homework, and for 5. I don't have a homework assignment here. I say in the schedule, I'll announce it. So what I think you should do, and I think you're gonna find this homework a lot easier because you're just finding definite integrals, right? You're gonna be using this theorem. Page 289. And then probably do like, 1 through 20, try like 1 through 21 odd. It's just so you can practice. So you can practice, setting things up, getting your notation right, plugging in the two numbers. The integrals should be easier. Do not start anything else in any other section. Just do those. We'll come back and do more next week. Hopefully face-to-face. Any questions?
Do you have time to go over number 21 from 6.3?